guys, so I'm gonna do a generalized proof of the partial fraction decomposition method, also known as the cover map method. So Black Pen Red Pen did a video on this already, where he used this specific example, and basically he used the cover map method to find all these B1, B2, B3 terms. He wrote ABC, but I wrote B1, B2, B3 because it's a function of which term it is, as in like which position it is. So B of 1, B of 2, B3. And in principle, you only have a finite amount of letters in the alphabet, but it's irrelevant. So in general, when you're facing a fraction here with a bunch of factors in a denominator, and on the numerator you have some function of x, but in general the numerator has to be a polynomial. This is because you can't really write, if it's like sine of x or something, then you can't really write what should I call it, a real number in terms of sine of x, or as in sine of x in terms of real number. So it has to be a polynomial, the term on the top, which can be generalized as the series from k equals to 1 to n, as in how many terms are in the polynomial. And I'm going to denote that as n1 because there's different terms on the top than on the bottom. So we have some arbitrary sequence a of k times x to k. So in this case, a of 2 is 2 and a of 1 is negative 1, and all the way goes up to n1 equal to 2 because it's two terms. Now with that out of the way, we just write this as f of x over but what's on the bottom. We have a product of all these factors, and as Black Pen Red Pen specified, you can't have a power here since it's hard to find the zeros of the power, and I'm gonna show you why later. That's why that's true. So you have some arbitrary product here from k equals to 1 to n, as in how many terms there are. In this case, there's 3 terms of x plus a k, or a of k, whatever you want to do. English. So this can be written as a series here from I equals to 1, because I want to treat this differently or independently from this, brackets and all the way up to n, because there's n terms here, from I equals to 1 to n, and you have bi on the top and x plus ai on the bottom. Now we can write this out, and we must find bi. So we can expand this product first, which can be written as x plus a1 times x plus a2, and then dot dot dot, and there's some term between the last term and the first term, some arbitrary term, x plus ai, all the way up to x plus an is equal to b1 over x plus a1 plus b2 over x plus a2 dot 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 bi over x plus ai dot 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 plus bn, x plus an. Now this is pretty long here, so just bear with me, and I'll just scroll through here frequently. So we want to find bi here, and how we do that is we don't have any bias towards bi in particular. It's just any term here. In this case, it's bi. It could be b1, b2, bn, anything. So we're trying to be generalized here. Now, suppose if you multiply all these terms by this denominator on the bottom, x plus ai, then you shall acquire f of x times x plus ai over x plus a1, x plus a2, x plus ai. Now these terms, they cancel out all the way up to x plus a n is equal to b1 times x plus ai over x plus a1 plus b2 times x plus ai or x plus a2, and you get bi times x plus ai or x plus ai. These terms cancel, and you get all the way up to bn x plus ai or x plus an over there here. Okay. So suppose if we plug in negative ai into all these x's here, it shall still satisfy the equality, since we already made the assumption that there must exist some bi, some real numbers that'll make this equality true. So you get f of negative ai over a1 minus ai, a2 minus ai, all the way up to an minus ai, which is equal to, if we plug in ai into here, this will become 0. So if you plug in ai here, negative ai speaking, namely, this becomes 0. So it's going to be 0 times b1, which is 0. 0 over x plus a1 will be 0. So you just get 0 times b1 over, doesn't matter what's on the bottom, this entire term cancels out, plus 0 times b2, doesn't matter what's on the bottom, or you could just write it as a2 minus ai, a1 minus ai, but that all doesn't matter. This all cancels out, and you have only one term remaining, which is bi. Everything here to the right is canceling out. So there we have it. We have f of negative ai over this entire thing, which is a1 minus ai, a2 minus ai, an minus ai is equal to bi. Now, how do we generalize this further? We have a product here, and this is messy to write. How about we do something like this? We can just, why would we just plug in the following. Limit as x approaches negative ai, x plus ak here, from k equals to 1 to n. So the reason why I evaluate this as a limit is because if you plug in negative ai into here, this term will become 0, and you have x plus ai somewhere here. So you get a 0 term on the bottom times 0, and that'll become undefined. So that's why I did a limit. So formally, bi, any term in this sequence can be written as so.